wanna get to this part, which is the sort of, how do you pick what you should do? And this is the short version, right? Like, if you just want to dump your data somewhere so that you can analyze it, and you're getting it from some APIs or something, or you already have it in JSON, just dump it into Mongo, and then you can process it all later. If you know that you're like writing a web app that has a lot of inserts and a lot of queries, and it is a structured problem, then use SQL, right? That's sort of basically the guideline of how you pick. If you have a bunch of objects and properties, you're probably going to end up with SQL. Now, if you don't need to do a lot of joins, and you're just sort of storing stuff to look up later, and you only need one analysis, you might be better off with Mongo. Why would you make these decisions? Document databases are flexible and easy to start with, but they can be harder to sort of really analyze. You need to learn a little bit more to really analyze the data in them, right, to do complex analysis. For relational, the same bits that I've already said. Modeling's super important to get it right. And as I'll talk about later, like naming things is really important. Like come up with some conventions and stick to them. So this is the basic instruction of how you make decisions about what you want to use. There's libraries that are great for each. Like in Python, Mongo has a PyMongo library that works really well to insert stuff and to query against it. One of the reasons that people use Mongo is that it lets you use MapReduce. So if you have data that you need to analyze and you have lots of it, like millions of records, one great way to analyze it is to be able to parallelize your analysis, right? So I think I've talked about before how like we have come to a point where it's cheaper to have tons and tons of cores in a computer than to have one really powerful one, right? And our software has gotten to the point where now people build software to let you parallelize your operations. Because since it's cheap to put a lot of different cores that can operate independently, if you can say, hey, I have 1 million rows to analyze, take the first 100,000, analyze them on that core. Take the second 100,000, analyze on that core. The third, analyze on that core. Go. Then suddenly you can analyze 300,000 at once in the same amount of time it would take to analyze 100,000, right? Because you're parallelizing it. MapReduce is a way to do that. It lets you basically split up your data and say, I want to run the same thing on all of it. That's the map stage. So the map stage is basically selecting the data you want to operate on, and the reduce stage combines it. And this was created to let you parallelize things so you can have super fast analysis of very large data sets. People don't really do this much with SQL. It doesn't really support it in that way. Mongo is a quick and easy way to be able to do that. There are other database engines that are built specifically to do this across 1,000 different computers with 16 cores each. That's one of the reasons this stuff exists. So that's so you know, because people talk about MapReduce because it's like all hyped about with big data stuff. I wanted you to know what that is. So I think, let's see, I got a couple other things. Oh, yeah, let me talk about, so now I'm going to get a little scatterbrained, if I wasn't scatterbrained already. I'm going to talk about 4 or 5 different concepts that are all connected to databases but aren't connected to each other that much, okay? So let me do one and then we'll take a quick break. So transactions. So remember we saw that word commit earlier, and I sort of glossed over what that meant. When you're doing things, sometimes you need to, in a relational database, sometimes you need to save like 4 things at once, right? So I want to save a person, I want to save a group, and I want to save a project all at the same time. And if one of them fails, then I sort of want to stop and not do any of them, right? This is what transactions were invented for. You basically start a transaction, magic green block, you start a transaction, then you do the statements you want to do, insert person, insert project, insert group maybe, and then you say end the transaction, and you commit this whole thing. And if any pieces of it fails, then it rolls back all of it, right? So it tries to do the first thing, it tries to do the second thing. If the second thing fails, it undoes the first thing, okay? So transactions are really important when you're saving data across things, because otherwise you don't want to end up in a situation where like you have the project, but you don't have the person that owns it. That's just a bad data situation. You want to know that everything's saved or nothing. So a transaction is a way that lets you roll up a couple of of these sort of database operations into one package and try to run the whole package and handle failures gracefully, so it undoes it, okay? Most of these libraries, when you say execute, anything you've added will automatically get rolled up into a transaction. So in SQL Alchemy, from the way I've been using it, it looks like when you package up a couple of inserts at once, it'll try to run all of those as a transaction and commit it to the database, and then you can tell it to roll back or not. A lot of libraries, you need to explicitly say, start a transaction, add these things to it, and then end the transaction, and then run this whole transaction as a transaction. Why is that? That's because transactions add an overhead, right? They add a cost. Because while I'm inserting the person, if somebody else is over here trying to insert something, depending on how it's written, they might need to wait until my whole transaction is done before they get a chance to insert, right? So transactions can be a performance cost, depending on how the system is written. In small systems, that doesn't matter. If you have 1,000 people using the same table at the same time, this sort of stuff matters. So when you're thinking about the architecture, you have to think about things like that. Like, okay, if everybody's writing into this table all at the same time, is this going to be a bottleneck for me? So stuff like that matters. Let's take yeah, okay. So I'm going to start with indexes. So we talked a little bit about indexes as they relate to relational databases, right? Like there's this, you want to be able to look stuff up quickly. And having a unique number is going to be a super helpful way because computers are really good at looking up numbers really quickly, not so good at other things. So what happens is, remember we talked in one of the first classes about trees as one of the data structures? There's this thing called a B tree that I want to get back to, which is basically a balanced tree. And what it is you end up with this tree of numbers, right? With nodes and children nodes. And this can be a super efficient way to find information, right? So imagine a list of numbers. This is a list of numbers. And what it does is it stores it in a system like this, where we have a root node, and these sort of have like the middle values in it. And there's 3 children in this case. There's children that are less than the lowest, right? So 7. All these numbers are less than 7, right? All these numbers are between 7 and 16. And all these numbers are more than 16, right? So that's the sort of rule for this simple B tree. And that means that if you want to find a number, you can make one quick decision here that narrows you down quite well, right? So if you're looking for 22, the first thing you know is, I need to go over here. And now I have a much shorter list to search, right? That's super useful because you can find stuff really quickly, right? And remember I talked about that big O notation stuff? This is like log n. So that means like if you have 1,000 records, you'll have to touch at most log 1,000 points to find it. So it's reasonably fast. It handles big data well. The problem is you have to keep this balanced, right? So anytime something gets inserted, you have to figure out where to put it. So there's a cost to an index, right? And the cost is on inserts. So when you add data to a table, you have to maintain the index. And that basically looks like this. This was a nice example I found on Wikipedia of balancing your tree, right? So you start at 1, and then the second thing is adding a 2, right? So you're still good. As soon as you add a 3, you have to split into children, right? As soon as you add a 4, you just stick it over there. As soon as you add a 5, you need to redo things, right? As soon as you have a 6, you're still good. As soon as you have a 7, now you need 3 layers of trees, right? So basically, as you insert data, you have to rebalance your tree. And that can be expensive. So inserting 1,000 things at a time in a table with a lot of indices, with a lot of indexes, can be an expensive operation because it's constantly maintaining these indexes. Why do these indexes exist? Because they can make queries super fast, right? Ooh. Yeah. They can make queries super fast. Knowing what your main query is, like if there's one web page that really everyone visits, or there's one piece of analysis that you're always doing, that's like one query that you're running over and over again, you want to, if it starts to get slow, you probably want to put an index on whatever columns it's filtering on, right? So for instance, with a primary key, that creates an index by default, right? But if you have a foreign key that you are often searching against in your table, that's not going to have an index, right? So you want to add one, and there's a special type of command that adds an index. It basically says create index on these columns. And then it creates a tree like that to keep track of things, right? This exists in both SQL and in SQLite and Mongo, you have indices, right? So you can add an index in Mongo on a property of your document to make it easy to search against that property. So basically anything where you have sort of the main thing that's happening over and over, you want to make sure that that query is as fast as possible. And the way you make a query faster is by, well, one way to make a query faster is by adding an index on it, okay? That's kind of all I want to say. There is a special command explain that can let you do query optimization, but I don't want to get into that because it's a pain. So the other thing I talked about was managing your schema, right? So managing the metadata that describes what your tables look like in relational databases can be a pain, especially if you're collaborating, right? If I'm working and you guys are working on the same database, if I add a column, I need to make sure that you know that I added the column and that you have some way to add that column, right? So how do you do that? You turn it into code. We have a really good way to manage code between distributed people, right? We have version control, we have Git. So they've started to call the thing that lets you make changes to your database schema in code, they call those migrations. So if I add a column, that's a new migration, right? And I write it in code, and then you do a git pull, and then you execute it, and it looks at the version of your database, and then it looks at the list of migrations, and it runs any that haven't been run yet. What else do I want to talk about? Oh yeah, conventions. So this is, again, a list of random things that you should be aware of. So use conventions in your databases because it'll make your life easier. These are the ones from Rails. So like they use plural table names. So people instead of person would be the name of your table. Your primary key always is called ID. Foreign keys are table name underscore ID. So people underscore ID would be a foreign key. They always add created at and updated at timestamps to every table. So there's always two columns, created at and updated at. And they automatically get set to the time that the row was created. And anytime you update it, it changes the update timestamp. That's just useful stuff to have around. I don't specifically care if you use their conventions, but use conventions. So if you have a database where one table is named meal and the other table is named people, that's not consistent, right? It should be meals and people so that it's consistent. This is going to help your life. So pick your convention and stick to it. I like theirs. They've gotten popular.